Questions have lingered for generations about the quiet heart of North America. Why does one of the world's largest freshwater systems occupy such an unusual shape? Why do powerful magnetic anomalies stretch across the continent like an invisible fingerprint left by an ancient event? Why have geologists spent decades peering deep beneath the forests, lakes, and plains surrounding Lake Superior in search of a structure hidden from ordinary view? The answers have gradually emerged from thousands of seismic records, gravity surveys, magnetic maps, drill cores, and decades of geological research. Together, they point toward an astonishing conclusion. Far below the waters of the Great Lakes lies the remnant of an immense wound in Earth's crust, a feature so vast that it extends for roughly 1,900 miles, or about 3,000 kilometers, across the middle of the continent. Scientists call it the Midcontinent Rift, an ancient geological scar that nearly split North America apart more than 1 billion years ago before nature abruptly halted the process. At first glance, nothing about the modern landscape hints at such a dramatic past. The Great Lakes region is often associated with forests, fertile farmland, rolling hills, and expansive freshwater coastlines. Cities, highways, and shipping routes have flourished across terrain that appears remarkably stable compared with active plate boundaries along the Pacific Ocean. Earthquakes are generally infrequent, volcanoes are absent, and mountain building has long since ceased. Yet modern instruments reveal that this seemingly quiet interior conceals one of the largest failed continental rifts ever identified on Earth. The structure was not discovered through a single dramatic breakthrough. Instead, scientists assembled its story piece by piece over many decades. Early geological mapping revealed unusual volcanic rocks surrounding portions of Lake Superior. These rocks differed significantly from neighboring formations in both age and composition. They consisted largely of thick accumulations of basalt, evidence that enormous quantities of lava had once erupted across the region. Initially, these volcanic deposits appeared isolated, but as more field studies expanded across neighboring states and provinces, researchers began recognizing an extraordinary pattern. Magnetic surveys performed during the 20th century revealed a long, curving belt of exceptionally strong magnetic anomalies extending from present-day Kansas northward through Iowa, Minnesota, Wisconsin, Michigan, beneath Lake Superior, and then southeast toward lower Michigan. Airborne magnetometers detected these anomalies because basalt contains iron-rich minerals that preserve the magnetic direction existing when the lava cooled. The magnetic signature was unlike anything expected from ordinary continental crust. Gravity surveys strengthened the mystery even further. Dense volcanic rocks buried deep underground produced subtle increases in Earth's gravitational field. When scientists combined these observations with drilling records and seismic imaging, an enormous buried geological structure gradually emerged. Rather than isolated volcanic centers, the data revealed an immense system stretching across the continent. The Midcontinent Rift did not form because two continents collided. Instead, it originated during an attempt by Earth's crust to pull itself apart. More than 1 billion years ago, during the Mesoproterozoic era, the ancient continent known as Laurentia occupied a very different position on the planet. At that time, the continents familiar today did not yet exist in their modern arrangement. North America itself formed only one portion of a much older continental mass, undergoing continual geological change. Earth's interior continuously transfers heat outward from its deep mantle and core. This heat drives convection within the mantle, where solid rock flows extremely slowly over millions of years. These motions create forces capable of stretching, compressing, and transporting tectonic plates across Earth's surface. Occasionally, mantle upwellings deliver additional heat directly beneath continental crust, causing it to dome upward and experience intense extensional stress. Scientists believe precisely such a process began affecting central Laurentia approximately 1,100,000,000 years ago. Rising mantle material heated the overlying lithosphere, weakening it from below. As the crust expanded, fractures developed across an enormous region. These fractures allowed magma generated within the mantle to ascend toward the surface. Once the process began, volcanic activity intensified dramatically. Instead of isolated eruptions, lava poured from extensive fissures stretching across hundreds of miles. Successive eruptions buried older flows beneath newer ones, gradually producing volcanic piles of astonishing thickness. In certain locations surrounding present-day Lake Superior, these volcanic sequences exceed more than 15 miles, or about 25 kilometers, in cumulative thickness, when both erupted lava and associated intrusive rocks are considered. Such extraordinary volcanic production required immense volumes of magma. Modern estimates suggest that the Midcontinent Rift generated well over 1 million cubic miles of igneous material, equivalent to more than 4 million cubic kilometers. That volume rivals some of the largest known volcanic events preserved anywhere in Earth's geological record. The landscape during this period would have appeared almost unrecognizable compared with modern North America. Instead of forests surrounding freshwater lakes, enormous lava fields likely stretched toward distant horizons. Rivers periodically crossed cooling basalt plains before becoming buried beneath subsequent eruptions. Vast fissures opened repeatedly as fresh magma forced its way upward through the crust. Yet lava represented only part of the developing system. As continental crust stretched, large fault blocks gradually subsided, creating elongated basins capable of receiving thick accumulations of volcanic rocks and sediments. These basins deepened progressively as extension continued, allowing still more lava and sediment to accumulate. Geologists describe this type of structure as a continental rift, similar in concept to the modern East African rift. There, portions of Eastern Africa continue slowly separating today. Volcanoes, earthquakes, and deep valleys mark regions where continental crust is gradually thinning. Given sufficient time, continued extension may eventually allow seawater to enter, producing a new ocean basin, much like the early stages of the Atlantic Ocean. Evidence indicates the Midcontinent Rift may once have followed a comparable evolutionary path. Had extension continued long enough, central North America might eventually have split into separate continental fragments divided by an expanding ocean. Instead, something remarkable occurred. The forces pulling Laurentia apart weakened before complete continental separation could occur. Rather than progressing toward ocean formation, volcanic activity gradually diminished. Magma supply decreased, extension slowed. Eventually, the rift ceased widening altogether. Exactly why this happened remains one of the most actively studied questions surrounding the Midcontinent Rift. One leading explanation involves changing tectonic forces operating across the ancient continent. Geological evidence suggests that while the rift initially formed under extensional conditions, later plate motions imposed compression across Laurentia. Instead of continuing to stretch, the crust began experiencing forces that squeezed the developing rift shut before complete breakup became possible. Another hypothesis proposes that the mantle plume responsible for heating the crust gradually weakened, reducing magma production until extension could no longer sustain itself. Without continued injection of magma, faults ceased propagating and the continental crust stabilized. Some researchers suggest both processes worked together. The mantle heat source diminished, while regional tectonic stresses simultaneously shifted from extension toward compression. Combined, these changes effectively terminated one of Earth's most ambitious attempts at creating a new ocean. Although volcanism ended, the enormous structural depression remained. Over millions of years, erosion stripped surrounding highlands while rivers transported immense quantities of sediment into the abandoned rift valley. Layer upon layer accumulated across its floor. Sandstones, conglomerates, and mudstones gradually buried the volcanic rocks beneath thousands of feet or hundreds to thousands of meters of younger deposits. Compression later inverted portions of the rift. Rather than continuing to sink, some sections experienced uplift along ancient faults. Yet the overall structure survived, preserved deep within the continental interior as a geological fossil recording an event that almost reshaped North America forever. Time transformed the landscape beyond recognition. Ancient mountain ranges weathered away, new sedimentary layers covered older formations, continents drifted across the globe. Dinosaurs appeared and disappeared. Mammals diversified. Ice ages sculpted valleys and eventually excavated the basins that would become today's Great Lakes. The glaciers responsible for carving much of the modern Great Lakes landscape arrived only during the recent geological past, within the last several million years. Massive continental ice sheets repeatedly advanced across North America, eroding rock surfaces and deepening pre-existing structural weaknesses. Portions of the Midcontinent Rift provided zones where erosion proceeded somewhat more efficiently because fractured volcanic rocks and associated sedimentary formations responded differently to glacial processes than surrounding crust. Although glaciers did not create the rift itself, they helped expose many of its rocks around Lake Superior while simultaneously excavating depressions that later filled with fresh water after the ice retreated. Consequently, the largest and deepest of the Great Lakes occupies a region strongly influenced by geological structures established more than 1 billion years earlier. Lake Superior today reaches depths approaching 1,333 feet, or about 406 meters. While glaciers excavated much of its basin, the ancient tectonic architecture influenced where erosion became concentrated. The lake therefore preserves not merely evidence of the Ice Age, but also echoes of one of Earth's oldest continental tectonic events. Even with these clues visible at the surface, the full extent of the Midcontinent Rift remained hidden for generations, because large portions lie deeply buried beneath younger rocks extending across multiple states and Canadian provinces. Unlike mountain ranges that dominate the skyline, this immense structure leaves only scattered windows where ancient volcanic rocks emerge above ground. Everywhere else it remains concealed beneath forests, farmland, cities, rivers, and thousands of feet of sediment. Modern geophysics changed that picture dramatically. Sensitive instruments capable of detecting subtle variations in gravity, magnetism, seismic wave velocities, and electrical conductivity have allowed scientists to reconstruct the buried architecture in remarkable detail. Rather than seeing isolated fragments, researchers now recognize a continuous geological feature stretching across the continent like an immense healed scar, preserving the memory of forces powerful enough to nearly divide an entire continent into two. Although the Midcontinent Rift ultimately failed to produce a new ocean, its geological influence did not end when volcanic activity ceased. Instead, the immense volume of volcanic rock in place during its relatively brief lifespan permanently altered the composition, strength, and physical properties of the continental crust. Even today, more than 1 billion years later, geophysicists can detect its presence because the rocks filling the ancient rift remain denser and far more magnetic than the surrounding crust. Modern seismic imaging, gravity measurements, and aeromagnetic surveys continue refining the three-dimensional picture of this buried feature, revealing details that earlier generations of geologists could scarcely imagine. One of the reasons scientists often describe the Midcontinent Rift as a giant scar is that it resembles the healed remains of an injury rather than an active wound. When skin heals after a deep cut, the scar records where damage once occurred even though the tissue has long since stabilized. Earth's crust behaves in a surprisingly similar manner over geological time. The fractures created during continental stretching eventually cooled, hardened, and became integrated into the continent, yet they never completely disappeared. Instead, they remain zones where the crust differs from neighboring regions in thickness, composition, density, and magnetic characteristics. Those differences provide researchers with a lasting record of an extraordinary chapter in North America's evolution. The volcanic rocks associated with the rift have also become an important source of valuable mineral deposits, as enormous quantities of magma cooled slowly within the crust. Heavy elements such as copper, nickel, cobalt, platinum group elements, and titanium became concentrated in specific layers and intrusions. Over millions of years, hydrothermal fluids circulated through fractures, further enriching some of these deposits. Portions of the Lake Superior region consequently developed into major mining districts, particularly during the 19th and 20th centuries, when copper extracted from Michigan's Keweenaw Peninsula helped fuel rapid industrial growth across the United States. The Keweenaw Peninsula itself provides one of the clearest surface expressions of the ancient rift. Thick sequences of basaltic lava flows, interlayered with sedimentary rocks deposited between eruptions, remain remarkably well preserved there. Some lava flows extend for dozens of miles or many tens of kilometers, illustrating just how extensive individual eruptions became during the rift's most active periods. Unlike the steep volcanic cones commonly associated with modern volcanoes, these eruptions produced broad sheets of lava that spread across vast areas before cooling, gradually building an immense volcanic province layer by layer. Researchers have also recovered evidence from deep drill cores that penetrated buried portions of the rift. These cylindrical samples provide direct records of rocks lying thousands of feet or hundreds to thousands of meters below the surface. By analyzing mineral compositions, isotopic ages, and chemical signatures, scientists have reconstructed the sequence of volcanic eruptions with remarkable precision. Radiometric dating consistently places the principal volcanic phase at approximately 1,100,000,000 years ago, reinforcing the conclusion that the Midcontinent Rift represents one of Earth's most significant Proterozoic tectonic events. The ancient scar has also become an important natural laboratory for understanding why some continental rifts succeed while others fail. Modern examples such as the East African Rift remain under close observation because they illustrate the earlier stages of continental breakup. By comparing those active systems with the fossilized Midcontinent Rift, researchers can evaluate the factors that determine whether extension continues toward ocean formation or instead comes to an end. The comparison has shown that continental breakup is far from inevitable. Even when enormous quantities of magma erupt and the crust stretches dramatically, changing tectonic forces can still halt the process before a new ocean basin develops. Although the Midcontinent Rift is considered tectonically inactive, that does not mean the region is completely free of earthquakes. Small to moderate earthquakes occasionally occur throughout the central and eastern portions of North America, including areas influenced by ancient faults. Most are far weaker than those associated with active plate boundaries, but they demonstrate that old zones of weakness can occasionally respond to modern stresses acting within the continental interior. Rather than indicating that the rift is reopening, these earthquakes generally reflect the slow release of stress within crust that still retains structural features inherited from events more than 1 billion years in the past. Another reason the Midcontinent Rift continues attracting scientific attention is its relationship with the Great Lakes themselves. While repeated Ice Age glaciers carved and deepened much of the present landscape, the pre-existing geological framework strongly influenced where erosion became concentrated. The resistant volcanic rocks surrounding sedimentary basins and ancient fault systems collectively shaped the topography long before the arrival of continental ice sheets. As glaciers advanced and retreated over hundreds of thousands of years, they exploited many of these inherited structures, contributing to the development of the modern Lake Superior Basin. The lake therefore reflects the combined effects of ancient tectonics and comparatively recent glacial erosion, rather than a single geological process. Advances in computational modeling are now allowing scientists to recreate the birth and evolution of the Midcontinent Rift in unprecedented detail. Supercomputers simulate mantle convection, crustal stretching, magma generation, and fault development over millions of years, testing competing hypotheses against observations gathered from the field. These models suggest that the enormous volcanic output required unusually high rates of mantle melting, while the eventual failure of the rift likely resulted from a combination of declining mantle activity and changing regional tectonic stresses. Although details continue to be refined, the overall picture has become increasingly consistent across multiple lines of evidence. Far from being merely an ancient curiosity, the Midcontinent Rift demonstrates that continents are dynamic rather than permanent. North America often appears stable on human timescales, yet its rocks preserve repeated episodes of assembly, collision, stretching, mountain building, volcanism, erosion, and renewal, extending back billions of years. The continent visible today represents only the latest configuration produced by an exceptionally long geological history. Scientists continue expanding that history with each new survey, each additional seismic profile, and every carefully examined rock sample. Instruments capable of imaging deep crustal structures now reveal details impossible to observe only a few decades ago, while improved laboratory techniques continue refining the timing and chemical evolution of the volcanic system. Every new discovery strengthens the conclusion that one of Earth's greatest failed tectonic experiments lies quietly hidden beneath the American Midwest and the Great Lakes region. Rather than signaling an impending geological catastrophe, this immense buried feature serves as a reminder of the extraordinary forces that once reshaped the heart of a continent. More than 1 billion years have passed since lava last poured across its widening fractures, yet the magnetic signatures, dense volcanic rocks, ancient faults, and immense subsurface basin continue preserving the memory of an event that almost transformed North America into two separate landmasses divided by a new ocean. Instead, the rift healed, the continent endured, and the scar became part of the foundation upon which forests grew, cities rose, and the world's largest interconnected freshwater system eventually took shape. Today, every new scientific study reveals a little more of that hidden legacy, demonstrating that one of the most remarkable geological structures on Earth has been quietly waiting beneath the Great Lakes all along.